Today we're going to continue looking at partial derivatives, and we're going to see in two cases how you can use them. We will do more of the applications later, and then we're going to look at the chain rule in multivariable calculus. So just like there's a chain rule in single variable calculus, there is a chain rule here as well. So tangent planes. Z equals f of xy is differentiable at a point if there is a tangent plane touching the surface at the point. Now that should be familiar to you. Go back to single variable calculus. You remember what we said? If a function is differentiable at a point, there is a tangent line there. There's a unique tangent line. So it's the same thing in multivariable calculus. It's differentiable at a point if there's a tangent plane there. It's not a line. It's a plane. Also, if the first partial of f with respect to x and the partial of f with respect to y exist and are continuous at the point, then f is differentiable at AB. So that is a way, if I ask you to show that a function is differentiable at a point, you need to show that the first partials exist and are continuous. So the first thing we're going to do is learn how to find the equation of a tangent plane at a point. Just like you did in single variable calculus, let's do it now in multivariable calculus. So it's a formula, very important formula. You need to outline that because it's something you're going to be using. The equation of a tangent plane to a surface, z equals f of xy at AB, is z minus f at AB equals the first partial of f with respect to x at AB times x minus a plus the partial of f with respect to y at AB times y minus b. So let's do an example and bring this up a little. Find the equation of the tangent plane to the surface f of xy equals x squared plus y squared at the point 1, 2. So you have to find the first partials at 1, 2. So let's find fx. Fx is just 2x. And so fx at 1, 2 means you're going to substitute 1 for x and you get 2. Similarly, fy is 2y. Fy at 1, 2 means you are going to put 2 for y and get 4. So we have the partials. The next thing we need is f at AB, so the value of the function at the point. So in other words, we want f at 1, 2. So you put that into the function, and this is 1 squared plus 2 squared, which is 5. Now put all that into the formula. Know that A and B are 1 and 2 respectively. So z minus 5 equals 2 times x minus 1 plus 4 times y minus 2. And you just simplify that. Z, and I'll bring the 5 over. 5 plus distribute 2x minus 2 plus 4y minus 8. Z equals 2x plus 4y minus 5. Okay, any questions? Let's do this one. Okay, so find the equation of the tangent plane to the surface z equals x to the fourth plus xy plus y squared at the point 2, negative 3, 19. Okay, so we need to find the partials. Now, you must be saying, why are there 3 coordinates in the point? Because they have already found the z value. The z value is what we found in the last problem when we found f at 1, 2. Okay, so we don't need to do that part. Okay, so let's find the partial of z with respect to x. Give me that, please, one person. Go ahead. 4x alone. Why 1? Partially differentiating xy with respect to x is just y, right? Now find the partial at 2, negative 3, 19. So you're going to put 2 for x and negative 3 for y. So 2 for x, that's 32 minus 3, which is 29. Okay, let's find the partial with respect to y. Can somebody else give me that, please? Good. X plus 2y. Find this partial at the point 2 for x and negative 3 for y. 2 minus 6 is minus 4. And as I told you, we already have the value 19, right? So going back to the formula above, it would be z minus 19, because it was z minus f at AB, right? Equals the first partial 29 times x minus 2, the second partial minus 4 times y minus minus 3 or plus 3. Simplify that. Z equals 19 plus 29x minus 58 minus 4y minus 12. Z equals 29x minus 4y. Okay, what's that? 19 minus 12, that's a 7 minus 51. Okay, any questions? Okay, I think it's your turn now. Okay, so fx is negative 4x plus 1 at the point equals negative 8 plus 1, which is negative 7. Partial with respect to y is 6y at the point. It is equal to negative 6. We have the z value, so the equation is z minus minus 3 plus 3 equals minus 7 times x minus 2 minus 6 times y plus 1. Z equals minus 3 minus 7x plus 14 minus 6y minus 6. Z equals minus 7x minus 6y plus 5. Any questions? Okay, let's move on. We're going to look at linear approximations or linearization. You may have remembered it by that word, linearization. What is this? So let me just remind you what it is, because you did that in Calc 1. So let's go back to Calc 1, single variable calculus. We say that y equals 2x minus 1 is the tangent line to f of x equals x squared at x equals 1. Okay, so let's draw a picture because you'd understand by a picture. So draw the graph y equals x squared. And then at the point where x equals 1, so let's say that's where it is, there is a tangent line here. Oops. So this tangent line, when you calculate it, it's y equals 2x minus 1. We say, so where you have that tangent line, we therefore say that this tangent line is the linear approximation or linearization of f of x equals x squared near the point x equals 1. What does that mean? If you had to draw this on your calculator and you had to zoom into here where the tangent line is, you would find that you will not be able to differentiate between the curve and the tangent line. They would seem to be one. So what this is saying is that near x equals 1, it has to be near that point, not anywhere else. Near that point, the curve and the tangent line are the same. So in other words, you can use the tangent line to approximate the curve near x equals 1. And it is called a linear approximation because the tangent line is a linear equation. Okay? So we say because at near that point the two coincide, we therefore say that x squared, which is the curve, is approximately equal to 2x minus 1 near x equals 1. And then what is the usefulness of that? Let me tell you, first of all, it was really useful in the time when you didn't have such extravagant calculators like you have right now. So therefore, if somebody wanted to calculate x squared where x equals, say, 0.9999, something like that. So let's say I wanted to do that, and without a calculator, instead of squaring 0.999, I could just substitute it into 2x minus 1. Why? Because 0.999 is close to 1, right? And the two of them are almost the same near 1. So why don't you do that? Take your calculator, check. When x is 0.9999, tell me what is x squared? What do you get? Square this, what do you get? 0.9999998. The 0.999. Now take this, multiply it by 2 and subtract 1. What do you get? They should be almost the same.
0.99996.
They're almost the same, aren't they? Right. Okay, so that is what linear approximation means. Okay, so now let's go to 3D. So if in 2D, the tangent line is the linear approximation of a curve near a point, then in 3D, the tangent plane at the point is the linear approximation of the function near the point. Okay, so this is that's the notation we're going to use. So the linear approximation, let's call it L of xy, is equal to this formula. Now, if you remember the equation for the tangent plane I gave you a while ago, this is equal to z, right? So we replace z with L of xy, which is called the linearization. It's equal to this formula, right? And so we say that f of xy, that should be an approximation, is approximately equal to this. Okay. Let's do some questions. Okay, so these questions are in two parts. The first part, explain why the function, take out this s. Explain why the function is differentiable at the given point. Then find the linearization L of xy of the function at that point. So the first part, if you go back to the first page of your notes, remember I told you, how do you check that a function is differentiable at a point? Find the first partials. If they exist and are continuous, then you have differentiability at the point. So let's check that. So let's find the partial of f with respect to x. Now if you notice, x natural log of xy minus 5 is a product. Right? So we have to use the product rule here. Partially differentiate x, that's a 1 times ln of xy minus 5 plus x times partially differentiate the natural log of xy minus 5 with respect to x is 1 over xy minus 5 times y. That's the chain rule again, right? Okay, now fy, similarly, we can just do that right away because y is inside here. So partially differentiate x natural log of xy minus 5 with respect to y. So the natural log, so that would be over xy minus 5. We've got an x, leave it alone. The chain rule means you partially differentiate xy minus 5 with respect to y, and you get times x. So this is x squared. And if you notice, both of these functions are continuous. Okay? So these are continuous and exist near 2, 3. So f is differentiable at 2, 3. Okay, the next step now, so that's the first part. Now find the linearization Lxy. So the formula is right there. So what we need to do, we need to do three things. Find the partials at 2, 3 and find f at 2, 3. So it's just like finding the equation of the tangent plane. So fx at 2, 3 equals, so put 2 for x and 3 for y. So we get natural log of 6 minus y, the natural log of 1, plus xy, which is 6 over 6 minus 5. And that ends up being 6. Yeah. Right away, let's find fy at 2, 3. That's 4 over 1, which is 4. Then find f at 2, 3. Put that into the function. So that's 1 plus 2 times the natural log of 1, which is 1. So finally, L of xy, the formula says, it's equal to f at 2, 3, which is 1, plus the first partial 6 times x minus 2, plus 4 times y minus 3. When you work that out, you get 6x plus 4y minus 23. Any questions? Okay. So do this one and go through it. It's the same thing. All you're doing, you check in to see, what's the first question again? Let's go back. The two things you have to do there. Oh yes, you want to see whether the function is differentiable at 1, 1. So all you need to do is to find the partials, the first partials, and say that they are continuous and exist at 1, 1. Done. Then you find the linearization. It's similar to finding the equation of the tangent plane. That's all. So you find L of xy. So let's do this. So fx 3x squared y to the fourth, fx at 1, 1 is 3, fy is 4x cubed y cubed, fy at 1, 1 is 4. You want to find, oh, now both of these you should say right away, since fx and fy are continuous and exist at 1, 1, f is differentiable at 1, 1. Okay, so you need to say that. Now we find the linearization. F at 1, 1 is 1. And so L at xy is 1 plus 3 times x minus 1 plus 4 times y minus 1, which is 3x plus 4y minus 6. Any questions? Okay. Now, I want to do an example whereby you'll see the usefulness of this. But as I say, it was more useful before when we didn't have these calculators. Okay? So let's do this. Find the linear approximation of the function f of x, y, z is the square root of x squared plus y squared plus z squared at 3 to 6, and use it to approximate this number, the square root of the sum of these squares. Okay? So let's find the linear approximation. We can do that. So we need to find three partials, right? So the partial with respect to x, let's write, let me just take this out. Let's write f of x, y, z as x squared plus y squared plus z squared to the half. Okay? Now we can find the partials, the first partials. So partial of f with respect to x is, so it would be, that's a chain rule again. So half times x squared plus y squared plus z squared to the negative a half times 1, 2x. This works out to be just x over square root of x squared plus y squared plus z squared. Okay? Similarly, you do the same thing. Fy ends up being y over the square root of x squared plus y squared plus z squared. And then f with respect to z, same thing, z over the square root of x squared plus y squared plus z squared. If you can see a pattern, that would simplify your work. Okay? Now let's find the value of these partials at the point. So the partial, first partial at the point 3, 2, 6. So that is equal to 3 over the square root of 9 plus 4 plus 36, which is 3 over square root of 49, which is 3/7. Partial of y at 3, 2, 6 is y, so that's 2 over 7. Partial with respect to z at 3 to 6 is 6 over 7. The next thing we need is the value of f at the point 3 to 6. So what's it again? Is the square root of the sum of the squares, right? So it's just 7. So now, so we're writing on the linearization, but we're gonna, because there is an approximation. Okay, let me not confuse you. So L of xyz is equal to 7 plus 3/7 times x minus 3 plus 2/7 times x minus 2 plus 6/7. You have a question?
Y minus 2 or x minus 2?
Y minus 2, I'm sorry. Times z minus 6. Okay, when you simplify that, you get 3 over 7x plus 2 over 7y plus 6 over 7z. Now remember, this is a linearization, so this is really approximately equal to f of x, y, z. All right, so
Is that also the equation of the plane?
right, so he asked me if that is also the equation of the plane. Yes, except that you need a z here. Z is equal to that. Well, not z, no longer z, it's w. Okay? Now, the question is asking us to find the square root of these numbers. Okay? Oops, we don't have much space. So the square root of 3.02 squared plus 1.97 squared plus 5.99 squared. So if you notice, that is just like the function, right? But instead of using the actual function, we can use a linear approximation and just take these numbers for x, y, and z and plug it into the linear approximation formula. And why can we do that? Because 3.02 is near 3, 1.97 is near 2, 5.99 is near 6. So this is equal to 3/7 times 3.02, or I'll say approximately, plus 2/7 times 1.97 plus 6/7 times 5.99, which is approximately equal to 6.9914. And if you want, you can check your calculator to see what's the square root of the sum of these squares. Hopefully they're close. Any questions?
When you get down to your second to last part, the constants don't matter anymore, or you don't have to distribute the 3/7 to the -3 or 2/7 to the -3.
Well, I just worked this. I just worked it out on the calculator. So
No,
On your L equals.
That is why you're not.
say that again.
Your L, X, Y, and Z.
L, X, Y, and Z here.
He's wondering why you don't take 3/7 and multiply by 3. Or the -3 to get
Oh, I just did oh, you mean how I got this? I just did everything. I didn't show my work.
it all cancels.
It all cancels. All the constants cancel. Yeah. Did anybody do this thing? Is it close to 6.994? What is it?
6.9914.
Yeah. So that is a good way. If you get a question like that, you can always check your answer to see if your linear approximation makes sense. The chain rule in multivariable calculus. So when do you use the chain rule in single variable calculus? To differentiate composite functions, right? You do the same thing here. But it's a lot more complicated, okay? So let's start off with a simple function. Consider z a function of x and y, and suppose x is a function of t and h is a function of t. So in other words, z is really a function of t. Suppose that f, g, h are differentiable. Then, how do you get dz dt? Now notice, this is not the curly d. This is the straight dy, because z is only a function of t. There's just one variable. But it is partial z partial x, because z is a function of two variables, times dx dt plus partial z with respect to y times dy dt. An easy way to remember this is by a little drawing. And it will make more sense when we go into more partials. So z is a function of x and y, right? And then x and y are both functions of t. So because z is a function of x and y, you will find partial z partial x, and you will find partial z partial y. Then because x and y are just functions of t only, then you will find dx dt plus dy dt and dy dt. So therefore, the formula says to find dz dt, you multiply these two on the left, multiply these two on the right, and add them up. I think that's an easy way to learn it, you know, if you recognize that. Okay, so let's do some examples. Suppose z equals x cubed y to the fifth, and x equals t to the fourth, and y equals t cubed. Find dz dt. So if you want to draw the thing on the side there, that might help. Okay, so that's partial z, partial x, partial z, partial y, dx dt, dy dt. Okay? So you need to find all of these, two partials and two derivatives. So partial z with respect to x is 3x squared y to the fifth. Partial z with respect to y is 5x cubed y to the fourth. Dx dt is 4t cubed. Dy dt is 3t squared. Make sure you put the curly d's the right places. And so the formula says that dx dt, you multiply partial z partial x times dx dt, so it will be 3x squared y to the fifth times 4t cubed plus then 5x cubed y to the fourth times 3t squared. And everything must be in terms of t. So put back into this what x is and y is. X is t to the fourth, y is t cubed. So this becomes 3t to the fourth squared is t to the eighth. Y to the fifth, that's t cubed. So that's t to the 15th times 4t cubed plus 5. X cubed is t to the 12th. Y to the fourth is t to the 12th times 3t squared. When you work all of that out, you get 27t to the 26th. So that's the first one. Okay, any questions? Okay, next one. Suppose w equals e to the minus x squared minus y squared, x equals t, y equals t to the half, find dw dt. So again, if you want to draw the diagram on the right, so w is a function of x and y, and x and y are functions of t. So you want to find partial of w with respect to x and with respect to y, and dx dt, dy dt. So we have to find these four. Again, partial w with respect to x is, can somebody give me that? What is that? Minus 2x times e to the minus x squared minus y squared. And similarly, partial w with respect to y is minus 2y e to the minus x squared minus y squared. Okay? Then find these derivatives. Dx dt is just 1. Dy dt is a half t to the minus a half. Now let's find dw dt. So from your little diagram there, you multiply these two on the right and add them. So dw partial with respect to x times dx dt is just the same thing. So minus 2x e to the minus x squared minus y squared times 1. And then you have these two multiplied together. Minus 2y e to the minus x squared minus y squared times a half t to the minus a half. And then when you are done, make sure you substitute the t for x and the t to the half for y. So this becomes minus 2t e minus x squared is minus t squared minus y squared is just t. That one we can leave it out. Minus 2y, so that's 2t to the half e to the minus t squared minus t times a half t to the minus a half. This works out to be minus 2te to the minus t squared minus t minus, the 2's cancel, t to the half times t to the minus a half is 1. So that's e to the minus t squared minus t, which you can factor if you wish, minus e to the minus t squared minus t times 2t plus 1. Okay? Any questions? Okay, try this one on your own. Okay, let's go over it. So it would have helped you if you had drawn the little diagram thing. Partial z, partial x, partial z, partial y, dx, dt. dy dt. Okay, you give it to me. One person give me partial z with respect to x, please. 2x plus y. Somebody else give me partial z with respect to y, please. 2y plus x. Somebody else give me dx dt and dy dt. Okay, so you multiply to get dz dt. So this would be 2x plus y times cosine t plus 2y plus x times e to the t. And then substitute, put everything back in terms of t. 2 sine t plus e to the t times cosine t plus 2 e to the t plus sine t times e to the t. Okay? All right, now let's go further. More chain rules. So what if you have x is not a function of t only? It's a function of more than one variable. What do you do? So in this case, we will have partials all the way. Okay? All right, so let's look at that. Okay. Let z be a function of x and y, x be a function of u and v, and y be a function of u and v. Suppose f, g, and h are differentiable. Then the partial of z with respect to u is that product, the sum of these two products. Partial of z with respect to v would be the sum of these two products. Okay, again, let me show you how you can draw a little tree diagram to help you to learn that better. So z is a function of x and y, right? And both x and y's are functions of u and v. u, v, u, v. So you have partials all the way. So this is partial z, partial x, partial z, partial y, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So what this is saying is that if I want to find the partial of z with respect to u, just follow the branches of the trees. So you'd go partial z, partial x times partial x, partial u. But there's another one here. So you'd go partial z, partial y times partial y, partial u. If you want to find partial z with respect to v, you take the product of these two branches, these two, and add them up. So if you can draw the tree, it is going to be so much easier for you. All right? So let's do some examples. Okay, so here we have z, a function of x and y, and x, a function of s and t. We need to find partial z with respect to s, partial z with respect to t. So let's draw our diagram on the right. So z, function of x and y, x, function of s and t. Same thing for y. And then put all your partials in there. Partial z, partial x, partial z, partial y, partial x, partial s, partial x, partial t, partial y, partial s, partial y, partial t. Okay, so now let's calculate all the partials, then we'll put everything together. You have a question?
The cable's coming up in the back.
Let's do partial z with respect to x. What's that? 2xy. Give me partial z with respect to y. X squared. Now let's go to the x. Give me partial x with respect to s. Give me partial x with respect to t. S. Let's go to the y's. Give me partial y with respect to s. What's that? With respect to s. 1. Give me partial y with respect to t. -1. Okay. Let's bring them all together. So now let's find partial z, partial s first. So look at the drawing and know what you're going to take. So let me put it in red. You are going to take these two, right? And you're going to take these two. You want to reach the s's. Okay? So multiply these two, and add them up. So this would be 2xy times t plus x squared times dy times 1, which is equal to, now really you should put this back in terms of s and t, like put back what x and s is. But if it gets too difficult for you to put back, you can leave it like that. Okay? If you check the book, you might see that they have left it in terms of x and y. But I think it's easy to put back x and y, so let's do it. So that's 2st times s minus t times t plus x squared t squared. Okay, so that's just 2st squared times s minus t plus s squared t squared. And you can leave it like that, okay? Now let's do partial z with respect to t. Partial z with respect to t. So follow again. So this time you're going, just do the same thing but go to the t's. So it will be partial z with respect to x times partial x with respect to t plus partial z with respect to y times partial y with respect to t. Okay, so that is 2xy times s plus x squared times -1, which is 2 x is st, y is s minus t times s minus s squared t squared. And this works out to be 2s squared t times s minus t minus s squared t squared. Okay, so some of these questions, the chain rule questions, can be pretty long. But if you draw a little tree diagram, it should help you quite a lot, okay? Any questions? We're going to do another example. Number 2. This one is a proof. So z is a function of x and y. X is a function of u and v, as you can see, a half times u squared minus v squared, and y is equal to uv. So note they didn't tell you what exactly z was. They just told you it's a function of x and y. And here's the proof. you need to show that u times partial z with respect to v minus v partial z with respect to u is 2 times x partial z with respect to y minus y times partial z with respect to x. Okay? Again, draw your diagram. So you have z, function of x and y. You have x, function of u and v. And y the same. Partial z, partial x, partial u, partial z, partial y. This is partial x, partial v, partial y, partial u, partial y, partial v. Okay, now what we're going to do, we need to find partial z, partial v, partial z, partial u. Okay? So let's do partial z, partial v first. So from the tree, this would be partial z with respect to x. Oh, before we do that, let me back up a bit. I'm doing too many things in one go. Let's take this out. Let's find the partials that we can find first, okay? So that I don't do too many steps in one. We cannot find partial z with respect to x or partial z with respect to y, so leave that alone. We can only find the partials for x and for y. So, can somebody give me partial x with respect to u, please? Anybody? You might want to distribute that. That's a half u squared minus a half v squared. And maybe you can see it better now. What's it? U, right? And then right away, can somebody give me partial x with respect to v? Minus v. Good. Now, why don't you give me partial y with respect to u? V. And partial y with respect to v is u. Okay, I think we have it. Now we can find what is on the right, on the left, sorry. So let's first find these partials. Partial z with respect to v. So let's follow. So you're going from z to the v's twice, right? So it would be partial z, partial x times partial x, partial v, which is minus v, plus partial z, partial y times partial y, partial v, which is u. Okay? So this is really minus v partial z with respect to x plus u partial z with respect to y. Okay? When you are done, now let's do the other one, partial z, partial u. Partial z, partial u. Follow your tree. So look at the u's and we take in the pairs. So it will be partial z with respect to x times partial x with respect to u, which is u, plus partial z with respect to y times partial y with respect to u, which is v. Okay, so if you want to, you can write it like that, just to be consistent. Okay. Okay, now let's put it all together. So we need to do the proof. So what we're going to do, take the left side of what we have to show, work with it, and see if we get what is on the right. That's how you do proofs, okay? So I'm going to say left hand side. LHS is left hand side. So the left side is U partial Z partial V minus V partial Z partial U. So I got that from up there, okay, what we want to show. So take what you just found, partial Z partial V partial Z partial U. Take what you just found and put it in place. Substitute it. So that is U times what you just found up there, minus V partial Z partial X plus U partial Z partial Y minus V times U partial Z partial X plus V partial Z partial Y. Okay, so let's simplify that. We distribute. So this is minus UV partial Z partial X plus U squared partial Z partial Y minus UV partial Z partial X minus V squared partial Z partial Y. Now always look back to what you have to get. Look back at the question. The question is asking you to show what you need to get is 2. Look at the beginning of the question. You want to get 2 times X partial Z with respect to Y minus Y partial Z with respect to X. So what you should do is to simplify this as much as possible. We have a partial Z partial Y, so let's put it outside. So we have a U squared minus V squared times partial Z partial Y minus, and there are 2 of these, 2UV partial Z partial X. Go back. Everything now we need to put this in terms of X and Y. Recall. Let me put this here. Note. At the beginning, look at the beginning of the question. We said that X equals a half times U squared minus V squared. And Y equals UV. That's what we said right at the beginning, right? Good. So what is U squared minus V squared in terms of X? Anybody? What is this? 2X partial Z partial Y, and UV is just Y, so that's minus 2Y partial Z partial X, and we're done. Just factor out the 2. X partial Z partial Y minus Y partial Z partial X. Done. These are proofs in mathematics. You take one side, work with it, and see if you get the right side. And that was, by the way, that was a very short proof in mathematics. It's very short. I have done proofs maybe about 5 to 6 pages long, or maybe even longer. It's just one question. Any questions? Okay, so you try this one. That's just like the one we did before the proof. Draw your little tree and see if you can get this out. In your final answer, you can leave X and Y in there, or it will look kind of nasty if you just put everything in terms of S and T. Okay, let's go over it. So let's draw the tree. Z, X, Y, st partial with respect to x, partial x with respect to s, partial z with respect to y, partial x with respect to t, partial y with respect to s, partial y with respect to t. Okay. One person give me partial z with respect to x, please. Somebody else give me partial z with respect to y. Somebody else partial x with respect to s. Cosine t. Somebody else partial x with respect to t. Negative what?
Sine t.
You miss it. It's not just negative sine t. Right. Negative x sine t. Great. Partial y with respect to s. Somebody else? And then partial y with respect to t is? Okay, let's bring them all together then. So what is partial z with respect to s? Can somebody tell me what you have? 2xy cubed, yes. Cosine t, yes. 3x squared y squared. Say that again? I'm not hearing you. Sine t. Great. And then somebody now give me partial z with respect to t, please.
2xy cubed.
2xy cubed,
Times negative s sine t.
So that's negative s sine t, yes.
Plus 3x squared y squared.
3x squared y squared.
Times
S cosine t. Okay? Right, and we can stop there. Yes. You can leave it in terms of x and y. That is fine. So the question is for the homework. We can leave. You can leave it in terms of x and y. That is okay.
Does our tree just get bigger for this last page?
Okay, let's look at the last one. How many variables we have there?
4, 5.
So z is still a function of x and y, but x and y are functions of 3 variables. So here the tree, you need to draw that tree, as you will get really confused. That's the beauty of the tree, okay? So draw the tree. So z, x, y, x, s, t, u, s, t, u, partial of z with respect to x, partial x with respect to s, partial x with respect to t, partial x with respect to u, partial z with respect to y, partial y with respect to s, partial y with respect to t, partial y with respect to u. Okay, and so you're going to follow the tree the same way. So let's calculate some partials. One person, give me partial z with respect to x, please. Okay, good. Somebody else give me partial z with respect to y, please. Sx squared, right? Now let's go on to x. One person give me partial x with respect to s. 1. Then partial x with respect to t. 2. Then partial x with respect to u. -1. Good. Now, let's go on to y. Partial y with respect to s, please. tu squared. Partial y with respect to t, please. Su squared. Partial y with respect to u, please. 2stu. All right. Okay, let's bring them all together. So, what's the question? We want, what's it again? Partial z with respect to s. What do we have here? Okay, so follow the tree. We need these two times these two. So, partial z with respect to x. So that is 4x cubed plus 2xy times 1. So let's leave out the 1. Plus x squared times partial y with respect to s, tu squared. Okay, let's leave it like that because I want to go further with this. We're going to find some actual values. The next one we need is partial z with respect to t. So again, follow the drawing. So we need the same 4x cubed plus 2xy times partial x with respect to t is 2 plus s squared times partial, where am I? I got confused there. Partial y with respect to t is su squared. You have to concentrate on this, you know. And then the last one, partial z with respect to u equals the same thing here. Now we need partial x with respect to u, so that's times -1, so put a minus in front, plus x squared times 2stu, so 2stu. All right, so let me go a little further with this. So this is my question. You have found the partials, so I would ask you, find the value of the partials when s is 4, t is 2, u is 1. What if I told you that? So you obviously you need to plug into the formulas that you have there for the partials, but you'll need to find x and y because your formula still has x and y. So you go back to the original. Where is it? Let me get it here. No, I don't have it. So need to go back up there. What is x and y? Okay, x is s plus 2t minus u. So let's find that first. So x equals s plus 2t minus u, which is equal to -1, which is 7. Give me what y is, please. Could you tell me what you have there? stu squared. So this is 4 times 2 times 1, which is 8. Okay, so we have that. So you just take all of these values and put them into the partials. So partial z with respect to s is equal to 4 times, ooh, these numbers are going to be big, 7 cubed plus 2xy, 2 times 7 times 8, plus x squared, 7 squared, times t, which is 2, times 1. Are you all working it out? Because I'm not going to work that in my head. I'm sorry. Is it big? I don't think it's going to be that big.
Definitely over 100.
Somebody did it already?
first one's 1582.
The first one is 1582.
Partial Z, partial S, I got 1580.
Okay, everybody got 1582. One person got that.
So all of the one people did.
Okay, I'll accept it. I don't have much space. Uh-oh.
First one did it actually can have the so I got that number. I'm like,
And you do the same thing for the others. So partial Z with respect to T is the same thing. So we should have as well written that down. You know what is that? This part here, 1480. So 1484 times 2 plus S squared, which is 49, times S, which is 4, times U squared, which is 1. What's that one?
Is 3164.
3164. And then finally, partial Z with respect to U is minus 1484 plus 2 times S squared, so 2 times 49 times 4 times 2. What's that one?
Negative 700.
Minus what?
700.
700. Any questions?